Hi everybody, welcome to my talk. I'll be talking about symmetric formulas for products of permutations. This is joint work with Benjamin Rossman. Our computational model and our main objects of study are Boolean formulas, which we will regard as unordered rooted trees, where leaves are labeled by variables xi or negated variables not xi. And we'll regard these as the inputs to our computation. Non-leaves are labeled by and or, and we'll call these gates. We'll be considering AC formulas, so formulas with unbounded fan-in. And here I have an example of a Boolean formula. So every n variable formula computes a Boolean function from 0, 1 to the n to 0, 1 in the natural way. And we know by probabilistic arguments that there exist Boolean functions requiring a formula size that's exponential, but the best formula size lower bound for an explicit Boolean function is not even cubic. So it seems that proving formula size lower bounds is a difficult problem. And in our work, we'll prove formula size lower bounds for a restricted class of symmetric formulas. To study the symmetries of Boolean functions and Boolean formulas, we'll look at the action of Sn on functions and formulas. So first, functions. The symmetric group Sn on n elements will act on Boolean functions f by simply permuting coordinates. So to get pi of f, the function pi of f, pi f, we'll first apply the permutation pi to the inputs to f, and then evaluate on those permuted inputs. Many important functions that we study are invariant under large subgroups of Sn. So for example, the symmetric functions, which only depend on the Hamming weight of their inputs, are fully Sn invariant. So parity, majority, more generally threshold functions are all fully Sn invariant. Certain graph properties are also invariant under the action of permuting vertices. So in the context of Boolean functions, we'll regard graph properties as functions from 0, 1 to the n choose 2 to 0, 1. And the action will be induced by permuting vertices. So functions such as connectivity, perfect matching, and click are invariant under permutations of vertices, and thus invariant under this action. So that's the action of Sn on functions, but we also want to define the action of Sn on formulas, and we'll do it similarly in that the action on the formulas will be induced by the action on the inputs. So here I have a formula, and I'm going to let pi act on the formula. Pi is the transposition of 5 and 7 and 6 and 8 multiplied together, and I'll take each input xi and send it to x pi of I. So here I sent x5 to x7, x8 to x6. And the important thing to notice here is that this left subformula is the same subformula whether acted on or not acted on. Because remember that we regard our formulas as unordered rooted trees. This will lead us to study the G-invariant complexity of Boolean functions, where G is some subgroup of Sn. We note that a formula is G-invariant if it's, we say that a formula is G-invariant if it's fixed by all elements of G. And every G-invariant formula we observe computes a G-invariant Boolean function. So for a G-invariant function f, we can ask the question of 1, what's the smallest formula computing f? And the size of that smallest formula will denote L of f. And we can also ask what's the smallest G-invariant formula computing F. And we'll denote the size of that formula by LG of F. And we'll observe that L of F is always at most LG of F, because any G-invariant formula for F is also just the formula for F. And I'll note here that there are formulas that are not invariant under certain actions. So for example, this formula, but I have two formulas here. Both of them compute the 2-bit parity function. However, this first one is fixed by this pi, which transposes 1 and 2. The second one, I've added this artificial asymmetry, and it will not be fixed by pi because this subformula will get sent to the and of x, not x2 and x2, which and there's no isomorphism, tree isomorphism that maps the new formula back to the old one. So we can ask the question of whether there exists specific functions f with large gaps between their invariant and non-invariant complexities. In other words, do there exist functions f that can be efficiently computed by formulas without breaking symmetry? So this question has been asked in other contexts, one of which is the field of descriptive complexity theory. And in this situation, it's known that there are functions that have large gaps between their invariant complexities and non-invariant complexities. So this is some related work to more work on symmetry and computation. Now, I'll state the problem that we're focused on, which is the computational problem of permutation matrix multiplication. And we'll denote this as a Boolean function, PMMKN, which, so the problem is the following. We're given m by n permutation matrices, M1 through Mk, and the task is to compute the 1-1 entry of their product. And this is a Boolean function from 0,1 to the kn squared to 0,1. For intuition and perhaps also visualization, we can think of this in terms of the action of the group of m by n permutation matrices on the set 1 through n. And all this problem is asking is, given M1 through Mk, does the permutation product M1 through Mk send 1 to 1? In the illustration, we see that 1 does get sent to 1. So indeed, M1 through Mk, the 1-1 entry of that will equal 1. There are well-known and conjectured optimal upper bounds for PMMKN. So the upper bound is that PMMKN is computable by formulas of size n to the O log k. To construct these formulas, we use a natural divide and conquer approach, which is to compute the matrix product M1 through Mk, we can first compute the matrix product M1 through Mk over 2, and then compute the matrix product with the second half of the matrices. So we end up with this arithmetic expression for the 1-1 entry. We then observe that we're working with permutation matrices, and so we can convert our arithmetic expression into a logical expression by replacing the sum with the or and the product with an and. At this point, we can apply induction to these subproblems, which which have small formulas computing them. And quantitatively, this will result in formulas of size n to the O log k. We'll now observe some facts about the symmetries of PMMKN. So we observe that PMMKN is invariant under the action of Sn to the k minus 1. The action is this shifted diagonal action where pi 1 through pi k minus 1 acts on M1 through Mk by sticking the pi 1 in between the M1 and M2, the pi 2 in between M2 and M3, and so on. The important observation about this action is that it preserves the matrix product M1 through Mk, because when we multiply out the acted on matrices, all the pi's will cancel with each other. We also observed that the divide and conquer upper bound formulas that I described are also invariant under Sn to the k minus 1. So we can restate our upper bound as PMM Kn is computable by Sn k minus 1 invariant formulas of size n to the O log k. So it's quite interesting that the conjectured optimal upper bounds for PMM Kn actually exhibit the same symmetry, some of the same symmetries that the problem PMM Kn exhibits. In our work, we prove a matching lower bound for symmetric Snk minus 1 invariant formulas for PMM Kn. So we show that Snk minus 1 invariant formulas for PMM Kn require size n to the omega log k. And this is tight up to constants in the exponent because the upper bound was n to the O log k. If we relax the restriction of Snk minus 1 invariance, or we get rid of that restriction, then the general form of our theorem would actually separate complexity classes NC1 in log space, which is good motivation for this work. The way we arrive at our theorem is actually via a tight size depth trade-off. We show that Snk minus 1 invariant formulas for PMM Kn of depth d plus 1 require size n to the omega dk to the 1 over d. And this is a tight size depth trade-off. I said that the upper bound divide and conquer formulas of size n to the O log k are conjectured to be optimal. So we can frame this conjecture in the following way. The conjecture says that breaking symmetry does not help solve PMM Kn. So more formally, the Snk minus 1 invariant formulas for PMM Kn are optimal within some constant in the exponent. And again, this conjecture would separate NC1 in log space if verified. Now I'll give a brief and rough overview of the idea behind the proof of our theorem. So I'll restate the theorem as follows. Let G be Sn to the k minus 1 and view this as a subgroup of Skn squared. Remember that Skn squared permutes the entries of all k n by n matrices. And then the theorem reads G invariant formulas for PMM require size n to the omega log k. To prove our theorem, we actually consider a larger group acting on inputs. This group is G plus, which is Snk times Snk. And the action is this left-right action, where given lambda and rho in G plus, the lambdas will act on the left of the matrices and the rows will act on the right of matrices. So this is the action of G plus on the inputs. So lambda for left and rho for right. Now we see that the action of Sn to the k minus 1 G, the shifted diagonal action of G on inputs embeds into the action of G plus on inputs as a subgroup of G plus. So the action of Snk minus 1 on inputs is really the action of the following subgroup G plus. The subgroup is given are those elements such that lambda 1 equals rho k equals the identity, and then rho 1 equals lambda 2, rho 2 equals lambda 3, and so on. So the action of G via the shifted diagonal is really the action of that subgroup under the left-right action. And this is that embedding. Then we construct a complexity measure on the subgroups of G plus. So for arbitrary subgroups H, we study the complexity of constructing H as the G plus stabilizer of a depth D formula. And we do this by induction on D. So you have some subgroup H, and you're interested in constructing a depth D formula whose G plus stabilizer is H. And I can tell you how big your formula needs to be, a lower bound on the formula size you need. So for example, the unshifted diagonal subgroup, which consists of those elements such that lambda1 equals rho1, lambda2 equals rho2, is constructible as the stabilizer of a small formula. So under our complexity measure, that unshifted diagonal subgroup has low complexity. However, the shifted diagonal subgroup will show has large complexity, and we'll also show that that implies that the shifted diagonal subgroup requires large formulas. So we'll actually focus on the subgroup ANK times ANK of G plus. Call that AN is the alternating group. It's a subgroup of SN. And the reason why we focus on AN rather than SN is because AN is a non-abelian simple group when n is at least 5. And because of this, Gorzat's lemma, which characterizes direct products of subgroups of direct products of groups, will give a useful characterization of the low index subgroups of ANK times ANK. So then the question is, well, why do we care about low index subgroups? And the answer is that we provide a connection between the index of subgroups and size of invariant formulas via applications of the orbit stabilizer theorem. So to use the orbit stabilizer theorem, we need some kind of group acting on a set. And to construct this group action, we'll consider some formula F, and we'll let S be its ANK times ANK stabilizer. Then we'll let F act on the set of subformulas of F. Because F is stabilized by S, it's invariant under S, this will induce the permutation action, a well-defined one, on the subformulas. So this is a well-defined group action. Now we know that the size of F is at least the size of the S orbit of any Fi. And by the orbit stabilizer theorem, this is equal to the index of the S stabilizer of Fi and S. So here's a connection between index of subgroups and size of invariant formulas. And so roughly we'll have two cases. If first this index of the S stabilizer of Fi and S is large, then we already have some good lower bound on the size of F, and we can say we're done. Otherwise, we roughly have that this index is small. So the stabilizer of Fi has small index in S. In this case, Gorzat's lemma will give a useful characterization of low index subgroups of AN to the K times AN to the K. There's roughly some relationship between AN direct product powers of AN and S. And we'll be able to say something about the size of Fi. We'll be able to say that Fi itself must be somewhat large. And in that case, the size of Fi, lower bounding the size of Fi will then again give us a good lower bound on the size of F. So we have some connection between index of subgroups and invariant formula size under using orbit stabilizer theorem. And then the part of our proof is to use this characterization of the low index subgroups to construct some kind of complexity measure on the set of subgroups of G plus. Quantitatively, this will give us the tight lower bound of n to the omega log k. So that's it. Thanks for listening, and I hope you enjoyed the talk.